Hello everyone, welcome to Physics Forum where your success is our mission. Now today we will talk about periodic trends and particularly the periodic trends in ionization energy of elements. So let's start by understanding what is ionization energy actually means. The energy required to remove the most loosely bound electron from an isolated gaseous atom, or in a simple term, it tells us how tightly an atom holds onto its outermost electron. The units are in kilojoule per mole. That means how much energy is needed to remove electrons from 1 mole of atom. For example, if we take sodium in its gaseous state and we want to remove 1 electron from it, so it will become sodium ion and 1 electron will be removed. You can imagine it in a way that you are trying to pull away an electron from an atom, and the stronger the attraction between the nucleus and the electron, the more energy is needed to pull it away. Now the question may arise here that why we use gaseous atoms to calculate ionization energy, why not solids or liquids? Now solids and liquids, their atoms or molecules are very closely held together. They experience different kinds of intermolecular forces like metallic bonds or van der Waals forces, which affect the energy of the electrons. So if we try to remove an electron from a solid or liquid atom, the measured energy would not actually represent only the atom's own attraction for the electron. So it would include external effects too. Hence we take gaseous atoms, where atoms are far apart and essentially independent of each other. Now let's look at the main factors that affect ionization energy. In other words, what makes it easier or harder to remove an electron from an atom? The first thing that affects ionization energy is the atomic size of the atoms. Now if an atom is smaller, that means the outermost electron is closer to the nucleus. That means its nuclear force acting on it will be more. So to remove it, we need higher amount of energy, so ionization energy will be higher. Now opposite to that, if the atom is large, on the other hand, having their outer electrons further away, so it's easier to remove one. So next is the nuclear charge. Nuclear charge means more protons are there in the atom, so more protons are there in the nucleus, so it pulls electrons more strongly. That means more nuclear charge equals to higher ionization energy. Next is the shielding effect. Shielding effect means inner shell electrons act like a shield, reducing the pull of the nucleus on the outer electrons. So when shielding increases, obviously the attraction decreases and the ionization energy becomes lower. Finally, the electronic configuration that affects factor that affect ionization energy. So if the atom that have completely filled or half filled subshells are more stable, because of this stability they resist losing electrons, so they have higher ionization energy. So overall, small size, stronger nuclear charge and stable configurations increase ionization energy, while greater shielding lowers it. Now let's see how ionization energy changes as we move across a period, that is from left to right. Here is an example of one period, that is the second period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So from left to right, how ionization energy changes. So as we go across the period, the atomic number increases, meaning the more protons are added to the nucleus, but at the same time electrons are added to the same shell and not a new one. So this makes the nuclear charge stronger, pulling the outer electrons closer to the nucleus. As a result, the atomic size decreases and electrons become more tightly bound as we go from left to right. So it takes more energy to remove an electron, which means ionization energy increases across a period. However, there are a few exceptions. For example, boron has a slightly lower ionization energy than beryllium, and oxygen is slightly lower than nitrogens. We will talk about this in detail in later slides. So these exceptions occur because of the stable electronic configurations, and the subshells make some atoms more stable and less likely to lose electrons. So the in general, ionization energy increases from as we go from left to right across a. Now let's see what happens when we move down a group in the periodic table. As we go down, we have one more electron shell added than the one above it. This means that outermost electron is farther away from the nucleus. Even though the nuclear charge increases, since there are more protons, the effect of that increased charge is largely cancelled out by shielding effect. Shielding of the inner electrons. The inner electrons block or shield the attraction of the nucleus from reaching the outermost electrons effectively. Because of this, the effective nuclear attraction felt by the outermost electron decreases, and it becomes easier to remove that electron. So overall ionization energy decreases down a group. Let's take an example. The first group, if we see the first group, lithium, sodium, potassium, rubidium and cesium. Group 1, lithium has the highest ionization energy. As we move down to sodium, potassium and cesium, the ionization energy keeps dropping, and that's why cesium is much more reactive, and it loses its outer electron very easily. So in general, across a period, ionization energy increases as we move from left to right, and down a group, ionization energy decreases. Now let's look at a few important exceptions. We're talking about exceptions in earlier slides to the general trend in ionization energy. We just learned that ionization energy usually increases across a period, but there are a couple of small dips that don't follow this rule. The first exception is between beryllium and boron. Now beryllium has an electronic configuration of 1:2:2, completely filled 2s subshell, which is quite stable. Now boron on the other hand has 1:2:2p1. Since boron's outermost electron enters are higher energy 2p orbital, it's easier to remove. So boron's ionization energy is lower than the beryllium's. This is the first exception. Now the second exception occurs between nitrogen and oxygen. Nitrogen has half-filled 2p3 configuration which is extra stable due to symmetrical distribution of electrons. Oxygen on the other hand has 2p4, one paired electron that causes repulsion between electrons in the same orbital. This repulsion makes it slightly easier to remove an electron, so oxygen's ionization energy is lower than the nitrogen's. So far we have discussed only the first ionization energy, that is the energy needed to remove one electron from a neutral atom. But an atom can lose more than one electron, right? And each time the amount of energy required changes. The second ionization energy, or what we call it IE2, is the energy needed to remove a second electron from singly charged ion. Similarly, if we talk about the third ionization energy, IE3 is for removing the third electron, and so on. So each successive ionization energy is greater than the previous one. And why is that? Because once you have removed one electron, the ion formed is positively charged, which means the remaining electrons held more tightly by the nucleus. So more and more energy is needed to remove the next electron. For example, take sodium. The first ionization energy removes its single 3s1 electron, forming sodium ion, which now has a stable noble gas configuration like neon. If we try to remove another electron from sodium, it has to come from inner completely filled shell. So the second ionization energy jumps sharply, significantly from the first ionization energy, and this big jump tells us that the first electron was in the outermost shell, while the next one is in much more stable inner shell. So studying successive ionization energies helps us identify the number of valence electrons and understand the stability of electronic conformation. So I have summarized everything for your ease in this slide. You can take a screenshot if you want. So let's practice some questions. First question is, among the elements beryllium, boron, nitrogen, oxygen and fluorine, that is all in period 2, the correct order of first ionization energy is, what will be the answer? Beryllium is boron is less than beryllium, is less than oxygen, less than nitrogen, less than fluorine. And we already know why it is like that. There are some exceptions, like beryllium has electronic configuration of 1:2:2, which is a completely filled 2s subshell, that is a stable configuration, and removing from an electron from 2s stable 2s orbital requires more energy rather than boron's 2p1, that is the outermost electron. It is in 2p orbital, which is higher energy and less tightly bound than 2s electron, so it is easier to remove. And the reason between oxygen being less ionization energy than the nitrogen, we have already discussed, because nitrogen has a stable configuration, electronic configuration. Next is the element having the highest first ionization energy among carbon, boron, aluminium and nitrogen. So the answer is nitrogen. And why is that? Because if we take boron, we know that last electron is in 2p orbital, 2p1. Carbon has 2p2 and nitrogen has 2p3, that is the half filled electronic configuration. And aluminium in period 3, it is in different period altogether, and it has its last electron in 3p1. So the most electronically stable configuration here among these elements is nitrogen. So the correct answer will be nitrogen, having the highest first ionization energy. The next question is, an element X has first ionization energy, that is 495 kilojoule per mole, and second ionization energy as 4563 kilojoule per mole. Identify X. So you can see from here that first ionization energy is much lower than the second ionization energy. There is a huge jump from its first to second ionization energy, means removal of first electron yields a stable noble gas configuration. And we have just talked about an element that after removing one electron that achieves stable noble gas configuration, that is sodium. Sodium has first ionization energy 495 kilojoule per mole, and after that it becomes sodium ion Na plus, and the second ionization energy will be large because Na plus is like a neon, so there will be a large jump. The given values correspond to that sodium, so the correct answer is sodium. So let's take up some few more questions. Next question is, which of the following statements is true about I1 trend? A, I1 increases down a group. B, I1 decreases across a period. I1 increases across a period and decreases down a group. And fourth is I1 decreases across a period, increases down a group. Now, by now you know the correct answer, I think. So the correct answer is C, that is I1 increases across a period and decreases down a group. This is what we have talked about in this whole lecture, right? So the next question is, the first ionization enthalpy of ionization energy of oxygen is lower than that of nitrogen, and the reason. We also talked about the explanation of this question. The first option here given is that oxygen has larger atomic radius than nitrogen. Second is oxygen has one paired electron in 2p orbital, causing an extra repulsion. That is the correct answer. In nitrogen has an extra electron, making it bigger. No, nitrogen is in higher period than O. No. So the correct answer is B. Oxygen has one paired electron in its 2p orbital, causing an electron-electron repulsion. So thank you. And next we will be taking electron affinity. So stay tuned.